Hey everyone, and welcome! We are going to pick up where we left off, connecting a game controller via Bluetooth to an ESP32 and use this connection to control LEDs, servos, and motors. I went ahead and made all the hookups, and I'll go over them with you real quick. Here's the pinout for the board I'm using, and I'll leave a link below for this exact board. Everything in purple are the pin numbers. Starting with the red LED, through its anode, I have a resistor, and then it goes to this jumper here. And if we follow this along, it's connected to pin 2 of our ESP board. The cathode is connected to this ground wire, which is then plugged in to the power rail of our breadboard along the ground rail. Then I have two servos, one that we'll use for the X-axis and one for the Y-axis when I thumb the right joystick. So this will move servo X and this will move servo Y. As a rule of thumb, you never want to power things like servos or motors that draw too much current off of your board. So for external power, I'm using this other power rail of the breadboard, and for each servo, I have power and ground and power and ground. Then their signal wires are going into the ESP32, one into pin 12 and the other one into pin 13. Finally, the motors. And to distribute power, as well as control speed and direction for both motors, I'm using the ever-popular L298N motor driver module. The positive and negative of each motor is connected to these screw terminals. These are our signal wires going to the ESP32. This very first jumper wire is connected to the ENA pin of the motor driver module, and that means enable A. So this will control the speed for motor 1, and that is connected to pin 14. Next, we have the in1 wire and the in2 wire. In1 or input 1 controls one direction, and then in2 controls the other. And so if you apply 5 volts to the in1, your motor is going to turn one direction. Applying it to the other wire will reverse the direction. So that's it for motor number 1. In1 and in2 are connected to pins 27 and 26. These wires are for motor 2. The first one is in3 or input 3, and then input 4, and then finally the speed wire, which is our ENB or enable B. In3 is connected to 25, and in4 is connected to 33. ENB is connected to 32. So we control the motor through these wires, and power is handled over here. These are 6-volt motors, and these 6-volt servos, so they can be powered from the same supply. And if you follow along, they're connected to the same power rail as the servos. And the last connection is that all of your components have to share a common ground back to the ESP32. And so for our external components, I have a ground wire coming out and coming into here. And if you follow that along, there is another wire over here. And that's the one that goes in to a ground pin on your board. I don't know about you guys, but I'm ready to get this thing moving. So you know what that means. To the code! I lied. There is one more connection. I don't see anything powering this set of rails right here. So for that, I like to use a female DC jack adapter, and I conveniently have jumper wires screwed into it, making it easy to run your prototypes. To handle our Bluetooth connection, we're going to be using the ESP32 library. And if this is your first time using the ESP32 board, there's a couple steps that you're going to have to take before you can just copy and paste this code. I encourage you to watch part 1. Link for that is below, where I take you through how to install the boards managers for both your ESP32 board as well as ESP32. And then after that, you'll actually have to install the boards. And then how to select the correct board. And then you can pick back up where we are here. All right, what's going on here? This sketch for controlling LEDs, servos, and motors is actually based off the BluePad32 example. So if you go under examples and then the BluePad32 controller. I always like to start every sketch by identifying my pin connections and creating variable names for them. That way, as my project gets bigger, which it always does, and you gotta move things to different pins, I have one place where I can update pin numbers and it gets reflected in the rest of the code. Next, we want to create servo objects because each servo needs a unique name. So you start by saying servo, and what is the name of your servo? I called mine X servo, and then the next one, I called him Y servo. This part of the code is part of the example. And so this portion here handles the connection to your particular game controller. So there's not much to worry about there. Here handles the disconnection. So we can skip that. Now this part is very important and hence I labeled it. And this is how you view what values each of your buttons, your joysticks put out, because we're going to need to use those values to then control different things. My PS4 controller has the D-pad right here, then the buttons, and that could be any button that you push as well as your trigger buttons. Then we have axis X, and this is for your main left joystick, moving left to right along the X axis. Next is the axis Y, so as you can imagine, it's moving up and down. And they're hinting at what values you can expect. -511 to +512. So one can assume that when the joystick is at idle, the value should be in and around 0. And for the X, as I thumb to the left, the value will go from 0 to -511. And then going to the right, 0 to 512. Up will go 0 to -511, and then down 0 to 512. And then it's the same for that right joystick. So axis RX and axis RY. Then depending on what you're using for your controller, there are other functions that you can tap into. The next area you want to pay attention to is this one right here. This is your controller action area. So this is where you tie components to certain buttons and joystick movements. It says process gamepad. So it's going to process what you assign. I'm going to skip this area for now because it's going to make a lot more sense later. So we're just going to keep scrolling down. And then towards the bottom, you can see the ever familiar void setup. Most pins on your ESP32 can act as an output or an input. And it doesn't know which one. So we got to tell it how we want each pin to behave. So for the LED pin, we want that to behave as an output. The ESP32 is going to be outputting that 3.3 volts when we press a button to light the LED. And all the motor stuff here, well, you can guess, that is output. We are going to be outputting information about speed, what direction the motor needs to be going. And finally, for the servo libraries, we need to attach each servo to specific pins. So it knows that my X servo is attached to the X servo pin, which we defined above, and the Y servo is attached to the Y servo pin. Then the rest of the setup stuff you can pretty much skip over. And in the loop, you'll notice the main call here, process controllers. When I scroll up above the setup, you can see process controllers right here. And it's going to start processing everything that you have connected. So process the gamepad. And if we continue scrolling up, we can see that it is referring to this section right here where all the action happens. But before we get into this section, let's just upload the code and see what kind of values that we're getting for our buttons and our joysticks, because that's going to be different if you're using some other controller than it is for me. So let's pop open our serial monitor here, and you see a whole bunch of different values going on. Jeez. All right. The first column to pay attention to is this D-pad, and you can see that it's followed by 0 times 0, 0, 0x00. 0. So you're going to get these values here. And look what happens when I press the up D-pad. I get 0, 1, the bottom D-pad 0, 2, 0, 8, and 0, 4. These are unique identifiers for each button. So it's important to go through your controller, go through this step, and just write it all down. For these buttons right here, if you look in the buttons column, you'll start seeing numbers changing. Same thing with your trigger. You can see that it's all controlled in that buttons column. Now for the x-axis, you can see that first axis L is mostly 0. Sometimes I get like a 4 in there. And this is super important if you are going to control things like motors, servos, or even lighting to see what kind of ranges you're getting at idle without touching anything. Because if you assign a value in this idle range and it's fluctuating, your motor can kind of like turn on, off, and do all kinds of things that you don't expect it to. As I thumb to the left, we're going to watch those values get even more negative. And let's see if it goes all the way to negative 511, like we were told up above. So here I go, all the way until I'm bottomed out to the left. And I get negative 508, so not quite 511. So make note of that. And when I return it, now we're getting an idle of around negative 16. Jumping to axis R, that very first column is our x-axis for that. So thumbing to the left on the right joystick should bring those values negative to negative 508. So at least both of them match on the left and on the right. And I'm going to thumb to the right and it goes to 512. And then thumbing up, it should go negative to negative 508. And then thumbing down should go positive to positive 512. So we know that our range is negative 508 to 512. And we're getting some different idle numbers for the right joystick and for the left joystick. So make sure to play around a little bit and write them all down. Now that we know how these values work, we can start assigning actions to them. So for instance, my PS4X button has a unique identifier of that 0001. So if the button value is equal to this, meaning I have pressed the X button, what do we want to happen? We want to digital write the LED pin high. So we want to turn on that red LED. And then if the button is not the X button, which means I have let go of it, well, I want the LED pin to turn off. And you can repeat this for all of the buttons and give each button its own action, but at least here you have a framework to activate and unactivate, disactivate certain components. And moving on to the left joystick. So in this case, I am pushing that left joystick up. So if the y-axis is less than or equal to negative 25, less than, that means these numbers are going to get even more negative. That confirms that I am indeed thumbing up on that left joystick. So what do we want to happen? If I'm thumbing forward, it would make sense to have our vehicle move forward as well. So we want both motors turning in the same direction. And maybe it'll be neat that the more I push forward, the faster it goes. Where does this negative 25 come from? Well, for the most part, if you watched the idles, it never really went below negative 25. So I want that to be my starting point for when the motors start to engage. To control motor speed, we're going to use PWM values, which go from 0 to 255 or 255. 0, of course, meaning not going at all, and 255 meaning pedal to the metal as fast as we can go. But the problem is that doesn't match up at all with values of negative 25 to maximum negative 508. So we're going to have to somehow map these values together. So in order to do that, I created a variable and we are going to map the values that we're getting along the y-axis, starting at negative 25 all the way up to negative 508. That means I am thumbed all the way up. And so we want negative 25 to equal a speed of 70. Well, why not 0, right? Because motors, for the most part, usually take a certain PWM before they even start moving. So you're going to be thumbing up and like nothing's happening until you get all the way to the end. So I know 70 for these motors is a good starting point. That's when they start thinking about that they want to turn. So as you thumb past that, then you're going to get a much more responsive vehicle. And of course, when I'm all the way thumbed up, well, I want the motor to be going at top speed, which is at 255. So now we have our values and we got to use them. As long as I'm thumbing up on motor number 1, we want the in1 pin to go high. and therefore the other direction in 2 pin of the same motor must be low. A motor can't go in 2 directions at the same time. Many motor drivers, if that accidentally happens, will engage a brake feature. So then for the second motor, we want to write the in 3 pin high. So these two are going to turn in the same direction, and therefore the in 4 pin must be low. And then speed for that first motor, the E and A pin, we're going to write it by the motor speed, which is whatever the heck was calculated in here, depending on where I am in the thumbing up process. And for the second motor, the E and B pin, we want to write it by the same motor speed. Next, let's thumb down on that left joystick. So now the numbers are going to get positive. So in the y-axis, if it is greater than or equal to 25, what do we want to happen? Well, first thing, we got to map that motor speed again. So we are going to map the y-axis starting at 25. I'm going to again map that to a speed of 70. And then when I'm thumbing all the way down, it'll hit 512. I want that to map to maximum speed of 255. So because I'm thumbing down, I want the motors to go in reverse. We're going to back up. So you'll notice that I simply reversed the pins here. So for in 1, we switch that to low, and in 2 to high. And then we do the same thing for the second motor. So they're turning in the same direction. And then for the E and A pin, we're going to write it by the motor speed that was calculated up here. And same thing for our second motor speed. So the more that I thumb down, the faster it's going to back up. And now something has got in our way. So we have to swerve left. And thumbing to the left means that the numbers are going to get more negative. So starting at -25, let's map it. You can see that the motor speed is always mapped similarly. It just depends on what direction your joystick is going. So in order to turn a car to the left, an easy way to do that is to hold your left wheel still and only move the right one. This will cause your car to jerk to the left. So you see me doing that here. Motor 1, which is that left wheel, I turn both direction pins to off. Essentially, it's in neutral or park. And then for that right motor, I've set in 3 to high to start turning it in the forward direction. And obviously then the other direction has to be set to low. And then for our left motor, I wrote a speed of 0. No one's stepping on the gas on that motor. And then for our second motor, the motor speed that is calculated here. And then the opposite is true for turning to the right. Now we want that left wheel to move and the right one to be still. And thumbing to the right means the numbers are getting more positive. So you can see the mapping here. It goes to positive 512 and we've mapped the motors. In this case, we want to move motor 1. So I set that in 1 pin to high and then the other one, of course, to low. And then for the second motor, I turned both direction pins to low. And then for the left motor, that one gets written with a motor speed while the second motor stands still. If you want your joystick to work reliably, it's important to carve out some kind of dead zone because you see that all of our movements either start at 25 or start at -25. Well, what the heck happens between -24 and +24? If you don't spell it out, the Arduino will just pick. And trust me, it's never what you want it to do. So here I am carving out that dead zone along the y-axis, thumbing up and down, so long as it is above -25 and below 25, so -24 to +24, as well as the x-axis also being in that same range. What do we want to do? We want to write the speed pins off. So your vehicle or your robot is not going anywhere. And for something different, I decided to use the right joysticks to control our servos. If I'm moving that right joystick along the X plane, I need to map those values to some kind of servo position. So we are going to map the entirety of the X plane from -508, which is all the way left, to +512, which is all the way right, to servo positions 0 to 180. Because when I let go of the joystick, theoretically, the servo should turn to 90 because that's kind of the halfway point. Then we take our X servo and write whatever servo position I happen to be at with the joystick. And then for the other servo, it's going to be controlled by up and down movements. So we're going to be mapping the y-axis of the right joystick to another servo position. And that, of course, goes from -508 to 512 and mapping it the full range of the servo. And then for the Y servo, we're going to write that servo position. So you can add functions to every button and joystick of your controller by using this method. Starting with the motors, I'm going to push up. So they should both be going forward. Then I'll push back. They should be going in reverse. And then right and left. Now let's go for the servos. Going left and right should control this black one over here. 0 to about 90 to 180. And if you're not precise, you'll activate that one. And you may be asking, why is that one jittering? The reason is because your idle fluctuates. Now, depending on the servo, sometimes it doesn't affect it too much. Other servos get very jittery. So how do you fix this? Exactly how we fix the motor. In this case, you would have to come up with separate movements for left and for right, and then for up and down, and create a dead zone where you hard code that dead zone to 90 degrees. And that should lock that servo into 90 degrees. And last but not least, our little LED by pressing the X button. There it goes. We're firing a missile or something like that. Maybe this is a battle bot. If you have any questions about the circuit or the code that you saw, I encourage you to post in the comments below. And for more personalized help, I invite you to join my community. Every week we have a live video chat where it's either a live workshop where we're deep diving into components, community build sessions where we all dedicate time to our projects together to get them across the finish line. And of course, the ever popular Arduino project challenges where we build and code together step by step in real time. Link for the community is below. Guys, I had a blast. But this is a long ways away from looking like some kind of battle bot. So I got work to do. Catch y'all later.